Hey folks, Chapter 14 completes our discussion on the water cycle where we focus on glaciers. This is a picture of the first glacier I ever saw with my own two eyes. This is the Franz Josef Glacier. It is on the South Island of New Zealand. It actually helped me understand so much about glaciers and glacial features. You know from lab that there's a tremendous number of glacial features. And this is a chapter that we'll definitely delve into those features and reinforce the ones that you learned in lab, but we'll also give you some more conceptual information about glaciers. Your textbook does a really nice job talking about glacial budgets and glacial movement, but for the most part you won't have to know about that in this class. We're going to focus on the types of glaciers, ice ages, and then both erosional and depositional features, because quite frankly there's enough content there to last us quite a while. So without further ado, let's start talking about types of glaciers. So these pictures are also from New Zealand. There are a chain of mountains called the Alps that are different from the European Alps that run down the South Island of New Zealand. And this is the highest point on New Zealand. This is called Mount Cook. I went there as an undergrad. I'm not going to tell you the year because that was a long time ago, but one of the things you can see is this U-shaped valley here. Remember when we learned about rivers, we talked about how rivers have V-shaped valleys when they're far from base level. When glaciers slide down through river valleys, they widen and deepen those V-shaped valleys and turn them into more U-shaped valleys. So you can see that here in what's called an alpine glacier. So it's just sort of coincidental that these are the Alps and this is an alpine glacier. Alpine glaciers are any glaciers that you find in mountainous regions. Here's another one of the alpine glaciers. You can see that there's a lot of sediment created by glacial erosion. So you'll learn about some of these depositional features where sediment is reworked and kind of shaped by glaciers, sometimes melted and transported by glaciers later on in this chapter. Alpine glaciers are generally pretty small, not relative to humans. Here's more pictures of alpine glaciers. But what's also true about alpine glaciers is that on a single mountain, you can have a couple dozen alpine glaciers. And as you move up in elevation, in general, the temperature gets colder, and so you tend to have ice year-round depending on temperature and elevation and precipitation patterns in mountains. And so that's where you have sort of the head of glaciers, and then they flow under the influence of gravity. Once they turn to ice and reach a certain thickness, they begin to flow downhill, much like rivers of ice, and they kind of erode sediment along the way. As they ease their way down mountains, they will widen and deepen some of these river valleys. But they do follow the path of least resistance, so they typically flow in old river valleys and then flow down them. So here's the group I was with. I'm not really sure why I was so far away for this picture, but all of the valley that you see here used to be covered in glaciers as well. Cool. So the other type of glacier is much different in scale. I just mentioned that a single mountain can have a couple dozen alpine glaciers. The glaciers we're going to talk about now are on a completely different scale, and those are called continental glaciers or ice sheets, and they, as the name implies, cover entire continents. So here we see the two remaining continental ice sheets on Earth. You see the one in Greenland, which is actually the remnants of the ice sheet that used to cover most of North America, well, a good chunk anyway, of North America about 20,000 years ago. And this is what remains. And then we have the Antarctic ice sheet, which is substantially larger than that even. But what you can see in general is the continental ice sheets or continental glaciers are completely different in scale. They're much larger. They cover entire continents in the case of the Antarctic ice sheet. They also behave kind of like pancake batter. They have a zone of accumulation where they're thickest, and then they kind of slump out in all directions, kind of like if you put pancake batter on a griddle and you have your central thick portion and then it kind of flows in all directions. That's kind of how continental ice sheets behave. So the last time continental ice sheets covered parts of North America really was during the last ice age. And this is a polar projection of what the Earth looked like during the last ice age in the northern hemisphere. So what you see here is the North Pole in the center of this globe. And what you see is actually the Greenland ice sheet right here, but here is a large ice sheet that covers North America. There was one that covered Europe and parts of Russia as well. And then you see sea ice throughout the Arctic Ocean. And here's what I was talking about with that really thick zone of accumulation, the thickest part of the ice sheet, and then it kind of slumps out in all directions. So this last ice age that we went through started about 2 million years ago, and there were some different pulses of it where it would get a little colder and a little warmer, a little colder, a little warmer, but ultimately ended about 10 to 12,000 years ago in New York. These ice ages occurred during a time period that geologists call the Pleistocene epoch. Perhaps some of you have seen the children's movies about ice ages. I believe is one called Pleistocene for that very reason. So again, the Pleistocene epoch occurred in geology on the geologic timescale from about 2 million years ago to about 12,000 years ago. During that time period, over 30% of land on Earth was covered in ice, which you can actually see a little bit better in this cool map. This is a Mercator projection, and it definitely distorts the amount of land at the North and South Pole, or the area really for the North and South Pole. But you can see that certainly all of Antarctica was covered with an ice sheet, as well as the majority of land pretty much from Pennsylvania on northward in North America. There are actually a series of alpine glaciers that are found in all the mountainous regions of the world as well. But the ice sheets itself covered the majority of well, not the majority, but a good chunk of land on Earth. This had tremendous impacts on organisms that were alive at this period of time. So this is an artist's recreation of some of the amazing megafauna that lived during the Pleistocene, including woolly mammoths, mastodons, giant sloths. There were tigers and camels and rhinos in North America. And most of these organisms ended up going extinct at the saber-toothed tigers, and I'm just rattling things off. Most of these organisms ended up going extinct at the end of the Pleistocene epoch for reasons I'll talk about in just a bit. One of the big things that happens during ice ages is that global sea level drops. And that's because a lot of water is being removed from the ocean and stored on land in the form of ice. And so during the last glacial period, sea level dropped approximately 250 feet, which nearly doubled the size of Florida because it has such a gently sloping coastline. What that meant is that lots of these big shifts in climate meant that organisms had to either migrate for food or basically stay there and die. And so there were areas where organisms were used to sort of grazing on shrubs and grasslands, and then those were covered in ice. So they all had to kind of migrate poleward. There were trees that no longer grew in the same areas. There were shrubs. When the food supply moves, organisms have to move. And then what happens is you have the convergence of organisms sharing much less land, which leads to more competition. It leads to transfer of disease between organisms. It puts organisms under a tremendous amount of stress. And so that led to some of the megafauna extinctions that we see during this time period. The other thing that happened is that during the ice age, the land was covered with a tremendous amount of ice. It's estimated that in New York that the glaciers were over a mile high, which is over 5,280 feet, and all of that ice exerts a tremendous downward pressure on the land, and it actually caused the crust to subside a reasonable amount. When that ice age ended and that weight of the overlying ice was removed, the crust began to rebound and bounce backwards. And what's interesting is that this is something we can actually still see today on the coastline along Lake Ontario. So here's Rochester, and this, for those of you who are in Rochester, know that this is Irondequoit Bay. And then if you go further to the east here, you'd end up in Sodus Bay. And right across Lake Ontario from, I'm sorry if you can hear my dog snoring. He literally won't stop snoring. I'm very sorry. Right across Lake Ontario from Rochester is the city of Toronto. One of the things that's been happening in Rochester in the last several years especially is we've had a lot of shoreline erosion. So there's a bunch of reasons why. There is a dam on the end of Lake Ontario which regulates the water discharge to Montreal. There's also been a lot of rain and snow in the last couple of years. Rochester was the snowiest city in the country this year. But the other reason is that Toronto is actually moving upwards. It's rising in elevation faster than Rochester is, and the reason is because of crustal rebound. So because Toronto is further north, there was the ice was even thicker in Toronto than it was in Rochester. So the weight of the ice was bigger in Toronto. So the removal of that ice has caused, even though it's over 10,000 years later, Toronto is still rising in elevation, and that's causing the water in Lake Ontario to slosh further south, and it drowns some of the river valleys here, and that's why Irondequoit Bay exists. This used to just be a river valley, but now with Lake Ontario being pushed further south because the northern shore of it is rising, then it's basically drowns the valleys on the south shore of Lake Ontario, which is kind of crazy. And still cool to see, well, unless you own property there or enjoy going to the beaches, which have been sad recently. This is actually believed to be the second reason for megafauna extinction. So around the same time that the ice age was ending, when there was again tremendous overhaul and reorganization of climate on land, humans first migrated into North America as well. And so there's evidence not only that organisms died because of tremendous climate change, but also because of human overhunting. There's been plenty of kill sites that have been located in North America where not all the meat was taken off of like a mastodon carcass, for example. So what causes the Earth to go into ice ages? There's a couple different hypotheses, definitely both of which contribute to ice ages. And the first is plate tectonics. So I teach historical geology, and we look at the Earth on a very different time scale. We look at all 4.5 billion years of Earth history, and what tends to happen is anytime you have a buildup of land masses, either around the northern hemisphere or around the southern hemisphere, there tends to be ice ages. And the reason is that any reason for there to be cold summers really will increase the chance for ice ages, because a cold summer means that in parts of the world there will be more snow that falls in the winter than will melt in the summer. And so over time that will continue to build up over thousands of years, and that what starts as maybe a small snow patch over time grows eventually into a continental ice sheet. A really good example of this actually occurred a couple winters ago when Boston, Massachusetts, one year got hit month after month with nor'easter storms in the winter, and they got a tremendous amount of snow. So eventually they ran out of places to store the snow, so they found one location, and all of the Department of Transportation of Boston piled up the snow in the same spot towards the end of the winter. And so in July, like 7 months into the year, is when that chunk of snow and ice finally melted. The thicker the snow is, the longer it's going to take to melt. So if you have a series of cold summers where there's a lot of land, whether it's the northern or southern hemisphere, you increase the chances of an ice age. Currently, most land is in the northern hemisphere. Over 70% of land on Earth is in the northern hemisphere. So we're actually, in terms of plate tectonics and the placement of plates, we're set up right now to increase the chances of there being ice ages. Another more complicated answer is that there are variations in Earth's orbit. And to be honest with you, They're very mathematical, but they're kind of cool. But what they all boil down to is that there are times in Earth history where we just simply receive less of the sun's rays. And the less the sun's rays we receive, the colder it's going to be on Earth. So this is summarized in what's called the Milankovitch hypothesis. The Milankovitch hypothesis is 3 separate cycles that all cause there to be, at certain times, less heat delivered to the Earth's atmosphere. And we're going to talk about the 3 types of cycles. I'm going to show you a short video that illustrates the 3 cycles.
Professor Richard Alley.
And the video will be starring Richard Alley, who's at Penn State University, who, this video is unfortunately a little pixelated, but Richard Alley is like a big brain in global science and climate change. He is pretty amazing. So here you go.
Penn State University investigates how the prehistoric temperature rises affected our weather. He's discovered that this wasn't a time of steady change. Instead, our climate was on an unpredictable and violent roller coaster ride of temperature highs and lows. It all started with a particular alignment of the planets in our solar system. 3 orbital variations, known as Milankovitch cycles, alter the amount of heat the Earth absorbs from the Sun. The first Milankovitch cycle that Alley considers is obliquity. The Earth doesn't stand straight up relative to the Sun, it tilts. Currently, it leans at an angle of 23.5 degrees. Imagine Alley's head represents Earth, and the lamp is the Sun.
So here's the equator going across my nose and the North Pole sticking out of a bald spot on top of my head. If the North Pole was straight up relative to the sun that I'm looking at, I could never get a sunburn on my North Pole bald spot. In fact, the North Pole is tipped over. Right now it's tipped over about 23.5 degrees. And because of that, I can get a sunburn here, and you can have sun in the Arctic in the summer.
But the angle of tilt varies over time.
It nods a little bit. And when you nod farther over, it's more sun at the North Pole, and this is the time when you melt ice. And when it looks up, the sun is at the equator, less at the pole, and this is the time to grow ice.
The angle of obliquity ranges between 22.1 degrees and 24.5 degrees over a cycle lasting 41,000 years. The second Milankovitch cycle is eccentricity. This time, a tennis ball signifies Earth, a clementine the Sun, and a hula hoop stands for the outline of Earth's orbit. The Sun's gravity pulls Earth in a nearly circular path. But when we move closer to Jupiter and Saturn, the gravitational forces of these 2 planets stretches our orbit into new shapes.
It goes from being almost round to being quite squashed and back to almost round.
This changes the distance that the Sun's heat travels to reach the Earth. It varies over a cycle that lasts between 90 and 100,000 years. The third Milankovitch cycle is precession. Precession is caused by the fact that the Earth is not perfectly round.
The real Earth, when it spins, bulges just a little bit at the equator. It certainly doesn't bulge as much as this one, but that bulge is acted on by the gravity of the sun and the moon, and one of the things that does is causes it to wobble around in a circle.
Just as the spinning top wobbles towards and away from Alley as it winds down, the axis of the Earth wobbles close to and away from the Sun. The toy completes its wobble in seconds, But the Earth takes between 19 and 23,000 years to go through a complete precession. Individually, the orbital variations of obliquity, eccentricity, and precession have a limited impact on Earth's weather. But over a 100,000-year cycle, these three oscillations combine to cause major temperature changes, leading to dramatic variations in global ice volumes. Ice ages, caused by changes in the Earth's orbit, have been a regular part of this planet's climate patterns for billions of years. The most recent ended some 20,000 years ago, when the Milankovitch cycles coincided to kickstart 10,000 years of global warming. Ali investigates the changing weather during this great thaw at the end of the last ice age. He uses environmental data preserved in the Greenland ice core.
An ice core is like a time machine. As it was drilled down through the ice, we're traveling back in time to see what happened.
Ali and his fellow time travelers make a shocking discovery. Earth's weather became hugely unstable at times during the 10,000 years of global warming. Temperatures rose by 6 degrees Celsius overall. But this was not a steady, gradual increase. The climate made a series of sudden short-term flips, dramatically switching from warming to cooling, and then back again.
What we're finding is that sometimes the climate is controlled by a switch. You push on it a little bit and nothing happens. You push a little more and it flops.
I love Richard Alley so very much. I'm not going to lie. He loves science. So, anyway, back to our science. There are 3 orbital variations that Dr. Alley just described, so we're going to go through them and then talk a little bit more about them in case you didn't pick up on all the fine points. So this is what Dr. Alley illustrated with the hula hoop, and that is that the shape of Earth's orbit around the sun varies over time, and it varies usually because of the gravitational pull of Jupiter. When we get closer to Jupiter, what tends to happen is that Jupiter pulls us a little bit further away from the sun, and we move from having a more circular orbit around the sun to having a more elliptical orbit. Just know that most of these diagrams are greatly exaggerated just so you see the difference here. So when the Earth has a more elliptical orbit, or it's a higher eccentricity, is the word that geologists use, it's physically further away from the sun, so it's going to receive less of the sun's rays. So circular orbit, less likely for ice age; elliptical orbit, more likely for ice age. And I put a star here because eccentricity or eccentricity is actually the most important of these 3 cycles. They all play a small role, but eccentricity turns out to be the most significant of these 3 Milankovitch cycles. The tilt of the Earth also varies, though not nearly as much. And that's because we have a big old moon that's fairly close to us, and that actually stabilizes our tilt. But the tilt of the Earth varies between 22 and 24.5 degrees, so not all that much. That's called the Earth's obliquity. But again, the more extreme the tilt, the more likely you are to have sun hit the North Pole. So when it's at maximum tilt, you are less likely to have ice age, and when you're at minimum tilt, you are more likely to have an ice age. And the orbital cycle and the reason the Earth kind of does this variation in tilt actually has to do with the formation of the moon, when the moon last sort of impacted us 4.5 billion years ago, and we're still kind of rocking a little bit because of that. So the very last cycle that varies over time, and so what Milankovitch did was show that these mathematically happened. When we started to get data from the ice cores, we really could see that that the cycles that we see in precession and eccentricity and obliquity, when those three cycles combine, is when we go into Ice Age, which is really kind of fascinating. We can see these Milankovitch cycles back hundreds of millions of years in the rock layers as well, which is super cool. So this diagram is always unpleasant for me. So this is supposed to be kind of like a kid's dreidel, but it looks like those things that you use to kind of suck snot out of babies' faces. But this is supposed to be like a dreidel. And as you saw in the video, it wobbles around. So right now when we look up in the night sky in the northern hemisphere, we can see the North Star, or Polaris, if you remember that from your high school earth science. It's not always that way because the earth wobbles. And so right now we're pointing towards Polaris, or the North Star, at night. But in like 12,000 years, we won't. In 12,000 years, we will be on the other side of this wobble. And when we look up at the night sky, if we were still alive, we would not see the North Star. We would see a different star called Vega. And so this really controls the season that Earth is in when it is closest to, when different hemispheres are closest to the sun. So here we are now, and this just goes to show you that not one of these cycles is a controlling factor, but all of them have some influence on our climate. Because right now, according to this, we should actually, if precession were in control of our whole global climate, we would be in an ice age. That's because here's the orientation of Earth currently. And so in January, we know that that is our northern winter, right? Because we're tilted away from the sun. We receive very indirect rays of light from the sun. And you can see in July, it's northern summer, and we receive direct rays of the sun there. But what you also notice is that we are much further away from the sun in July than we are in January. So right now, we're actually having colder summers in the northern hemisphere than we might in 12,000 years when the world looks very different. So right now we are having slightly colder summers, but fortunately we have a more circular orbit now, and we are relatively close to maximum tilt. So precession is keeping us slightly cooler than we might be, because in 11,000 years we will be in a very different orientation with the sun. But precession itself is not powerful enough to cause ice age. However, all the Milankovitch cycles together, when they combine, and when you have plate tectonics in the right location, they will create an ice age. So good stuff. So I know that you haven't done the activities yet, but this is really how the chapter is laid out. Isn't this beautiful? This is a picture of Glacier National Park, which is not a great place to see glaciers, oddly enough, any longer. And in fact, it's in northern Montana, and it goes into the Canadian Rockies also. It's predicted by the year 2030 or 2040, there will be no glaciers left in Glacier National Park, but it is an absolutely fantastic place to see glacial features and grizzly bears. It has the highest density of grizzly bears in the lower 48 states in Montana. It is wild. It is beautiful though. So today we learned about the different types of glaciers, and we also learned about ice ages. You have two assignments this chapter that they should sound a little bit familiar because they draw heavily upon your glacial lab. And the first assignment has to do with depositional features that form when glaciers slow down, when glacial meltwater slows down, and when glaciers dump rock and what's called glacial till and forms depositional features. And then the second assignment you'll do will be on erosional features, and those are the ones that you see at Glacier National Park, where glaciers are carving features from rock. Very cool. All right. Have a good time.